Hi, I'm Jonathan Cameron from Huawei, and today I'm going to be talking about what I would say I spend most of my development time on these days, which is Compute Express Link, CXL, a bit of a status update, a little bit of what's next, some ARM-related challenges. We had to have some ARM-specific content, but yeah, most of the challenges are more general, but we have some ARM-specific ones. Okay, so I won't bother talking about the outline because you're here watching the talk. However, I will talk about the notes. Yeah, I talk too fast. Uh, I'm almost incapable of stopping that, so it will go quickly. Um, I'd rather stop and have a discussion. So if you have questions, stick your hand up at any time. There's a lot of material here. I don't actually care if we get to the last couple of slides. There's some sort of supplementary, in case no one asks any questions, other things I can talk about to take advantage of the time. Obviously, there's an excellent corridor track with snacks and coffee and things. Do find me at that if you have any other questions. So, first of all, what is CXL? It's an interconnect standard under the CXL consortium, which has very wide membership. Pretty much everyone in the ARM ecosystem is a member at some level or other. Pretty much every other architecture, every significant device manufacturer, and every significant host manufacturer is there. It's very active, things move quickly. It's good. It's closely related to and built on top of PCI Express, which means whenever PCI Express gets quicker, CXL gets quicker. So that'll be happening later this year from a standards point of view. Obviously, it takes a little while for the hardware to actually turn up, and that's fundamentally because it's the same electrical side of things. CXL enables three key things. It enables low, latency memory access, which is going to be the main focus of today. I will note that we've had reports from some host vendors that the latency to CXL is actually slightly better than it is across NUMA sockets under some circumstances. So people always think it's terrible, and it's like, well, you use NUMA systems. You cope with that today. It's not actually substantially worse, depending on exactly what you build. It also enables coherent caching of host memory on devices, and the other way around, coherent caching of device memory on the host, which actually only really matters if you've got peer-to-peer traffic going on, or for some of the cases we'll come on to later. There is a thing called CXL Fabrics, which people get very excited about. It allows you to do thousands of nodes, really, really big, complicated systems, lots of communication between them. So far, there's no public software enablement around this. Always interested to hear if anyone cares about it yet. It will come, but it's a much bigger thing, so it's going to take a little while for adoption. And as I labeled it, the diagrams are mostly there because, as happened the other day, people complain I don't put pictures in my slides. So pictures. But more seriously, there's a couple of different sort of typical topologies there. We've got the one right at the top. That's kind of what people are building today. It's direct connect. You plug your memory devices or your accelerators straight into the slot on the motherboard. It's much simpler. It complies with earlier versions of the standards because switches came a little bit later. Second diagram down, we've got some switches. Third diagram down, we've got a switch that's actually shared by multiple hosts. And we have some devices that have a kind of hardware virtualization thing that lets you map them onto different hosts simultaneously. So you can map different parts of the memory to each host, known as multi-logical devices. It's in the spec, but actually, unless you're a switch vendor, most of the people are talking about the bottom one, which is kind of an optimization of that, where you get rid of the latency cost of a switch by using what's known as a multi-head device. And that's basically, think of it as a PCI card with a lot of connectors on the bottom, going to different hosts. This is something networking folk have done for years, but it's propagating out into this. And the reason is that you've only got one hop, lower latency. We'll come on to quite a bit about MHDs a little bit later. So, what's the key software? It's a rather software conference. So, fundamentally, kernel. That's why I like it. The kernel side of things, very healthy, multi-vendor. Overlaps with a number of other subsystems, memory management, things like perf. We've got PMUs and stuff. EDAC for RAS. We have a monthly sync call. If you're interested in this and you don't know who to get an invite from, just send me a message and I can forward it. We also have things like a Discord, and every year for the last 4 or 5 years, and there's one plan for this year. We've had a micro conference at LPC, focused on whatever the sort of upcoming topics are. And yeah, there's a mailing list. There's always a mailing list. Firmware. Now, the interesting thing about firmware for CXL was there was an assumption for the very early versions of it that OS enablement would take quite a long time. So the early specs, the 6L1, 1.1, was all written with the assumption the firmware did everything. And that propagates onto the later specs for backwards compatibility reasons. However, there's no open source version of it. There is some work from Fujitsu, I think. Actually, no, it wasn't. It was Fitium. Anyway, someone did it for EDK2 and SPSA QEMU model. Hasn't gone upstream yet. That's mainly, I think, for review from the SPSA model side of things. I think the 6L bit's fine. But nonetheless, there's something there, but it's quite minimal in what it does. It kind of stitches things together. It doesn't do the full firmware flows for OS agnostic stuff, which quite frankly are hard. There was code from ARM a long time back. There was a sort of thing on one of their reference platforms that works, but there was no continuation of that to upstream it so far. It may come. QEMU emulation. Now, I talked about this at Connect 2 years ago. We've added features since then, but if you fundamentally want to know about it, watch that talk. It's a key platform for ecosystem development. We run ahead of both hardware by quite a way. We actually run ahead of the kernel too. And that's because it's a well-defined spec. We know it's coming. There isn't the usual constraint you get with QEMU where they're not particularly happy at merging things until the kernel support's there because you need to test it, etc. So while we're doing the kernel development, we'll often upstream the QEMU stuff. It's usually simpler, actually. But there's also fabric management stuff going on, lots of projects around that. It's complicated to manage. There are lots of new standards, bits of redfish and things like that. Yeah, it's not quite clear who's going to win in that from the point of view of different projects. So watch this space for that. Okay, current generation hardware. So this is what has been certified. There's been quite a few announcements that a number of hyperscalers have certified products from all the major memory manufacturers in the last couple of months. They've all sort of been coming out one a week at the moment. And yeah, it's kind of expansion of conventional NUMA. This is all about that direct connect case we showed earlier. You can use switches if you want high fan out, but latency costs. So unless you need an awful lot of memory, people are generally not using switches. Common use cases for this. Oddly enough, there's quite a lot of workloads that are really, really latency insensitive. They're very easy to prefetch, or they parallelize very, very well. You don't actually care that latency is worse. All you care about is bandwidth to memory. Bandwidth to memory on a conventional server socket is limited by how many DDR channels. The most anyone's done yet is 12 per socket. It's quite a lot of bandwidth, but people want more because they're putting more and more cores down. Like the Ampere folk have talked about just how many ridiculous number of cores they have. Feeding that monster is hard. And so if you're very memory bandwidth intensive, then 6L memory can help a bit. So the systems people have talked about are adding another quarter, another third of the bandwidth to the system. All good benefit because it means you can use a third more CPUs effectively. And there's technologies around weighted interleave to deal with the misbalance of the different bandwidths. And that's a big piece of work that's gone on in the kernel. Another option is capacity expansion. Yeah, just plug more RAM in. An interesting one is technology mixing. So the hyperscalers are actually being quite vocal about this. They have a problem, which is memory's fantastically expensive. They also own an awful lot of it. Unfortunately, whenever a new server generation comes out, a new DDR spec, and you suddenly have however many billions of dollars of DDR4, which goes to the recycler. So what they're actually keen on doing is racking that up. And for some use cases, it doesn't matter if you're fairly insensitive to just how quick it is. You don't need some of the new features that come in the latest DDR specs. You can get a good benefit from doing this. So this is something that people have talked about a lot. I don't know how much of it's happening yet. Obviously, the memory manufacturers hate it. No, you need to buy the new stuff. But never mind. So there are some folk who just build memory controllers to stick in front of the memory, and they're very keen on it. Yeah, this stuff's present at boot or hot pluggable. We do have advanced RAS for this, which we might get onto if I talk very fast. Otherwise, we also have things to do with tiering assistance. So if you're trying to decide where to put your data, whether it is stuff that needs to be in that low latency memory or needs to be further out, CXL at the moment has the only published hotness monitoring unit spec, which is kind of an advanced form of performance monitor. It's going to be fascinating to see how we actually use those. A lot of discussions about that going on. Anyway, some architecture-specific stuff. So, 2 architecture corners to get us going. One is there's a weird quirk with memory hot plug, which is in the ACPI world, the where am I hot plugging the memory is actually in the event. The BIOS tells you it's on NUMA node 3. Yeah, that doesn't happen with CXL because it's a device and it's surfacing it later, it's all OS first. That information is available, but it's kind of available by doing a lot of, well, there's 2 things. You can either get the actual information on latency and bandwidths and create your own description. That's not what we do, because it's hard. We do present that description, but we don't use that to work out what NUMA node to put it in. We do the NUMA nodes based on some assumptions of stuff that comes from ACPI. And it's kind of reasonable. I think, as I say at the bottom here, I think it'll need revisiting. But for now, it works. But the only solution that worked for that was x86 specific. Interestingly, there was an attempt to generalize it about 8 years ago, at which point the maintainer rejected what he then did when we went back and asked him again. So what we've done is taken the infrastructure. This is Mike Rappaport who did it, who's now at Microsoft but wasn't at that point. He took the NUMA memblock stuff, generalized it a lot. It now works on a whole bunch of different architectures. I think they added long arch in the latest cycle. And it solves this problem. So thanks, Mike. Solve that problem for us. Next one. This gets a bit more complicated. So cache flushing by physical address. On ARM, as of today, this isn't really a thing. We'll come on to how that's solved. x86 has a solution for this. It's a lovely instruction. It's write back and invalidate all. Can only be issued by the kernel. When it says all, it means all. So every socket in the system, dump everything from every cache. As you can imagine, this is a little bit expensive. You watch your entire machine grind to a halt for, I don't know exactly how long, but it's getting towards seconds. So this is not popular. It took quite a lot of effort for them to persuade the kernel folk to allow them to call the instruction. And it was like, well, it doesn't work otherwise. But it's fine if you're not doing it very often, and it's very controlled. As I say, no such instruction on ARM64. The general view from talking to the ARM architects about it and things is that we want to do it as consider it a system problem. It's not actually a CPU problem. It's not something where an instruction is necessarily the right way to go. So, why? So normal cache coherent systems, you can assume that once you get down to a physical address and you read from that physical address, you're always talking to the same memory. Long comes 6L, no longer true. What we actually have is we have another layer of translation below the physical address going out to what is ultimately a device physical address, and there's interleave and all sorts of mess going on around this. And the problem is, over time, that mapping can change. It doesn't change very often. This is usually we've removed a device and we've plugged in a new device. There's another case that causes even more trouble. But the upshot of this is you can have stuff sat in the cache, and if you don't have this flush by PA, it's not mapped anywhere necessarily. You could have destroyed all the virtual mappings. You can create one in order to flush it, but then there's a race condition that means that doesn't work either. So you need to flush by physical address. You actually need to do it twice, which is even more fun. And then, yeah, that solves this problem. So that's why we need to do it. The annoying corner case is prefetchers. You didn't even need to have any memory there in the first place. Prefetchers are evil. They can fetch anything by any type of address whenever they feel like it. So they may decide to fetch for your L3 or whatever. They may go out there and they may fetch from a physical address where there isn't any memory. Now, the way this is handled in CXL, because you've got to do something if that happens, you get a request. You just go, well, yeah, it's garbage. Have a 0. I mean, we get error records and all sorts when this happens. It's not supposed to happen much. Actually, for prefetchers, you try to avoid error records, obviously, because they don't really exist. The problem is, we now have a 0 in our cache. We then map some memory. We think, oh, we're the kernel. We don't really trust anyone who gives us memory. Let's zero it. We write a 0. It goes, oh, it's already a 0. It's clean in the cache. Doesn't write anything. Then it's clean. Cache drops it, which they're always allowed to do. Whoops. We've now declared that thing to be 0 without it being 0. So we absolutely need some solution to this. And this sort of stuff has evolved from various discussions with some of the folk on the ARM kernel team and some of the architects. What we require is a means to flush by PA. It's a disaggregated problem in your typical ARM server. You've got to talk to a number of units, and the reason for this is that we've got interleave going on at all sorts of different levels in the system. It may be the cache directories are actually effectively interleaved because the caches are covering different parts of the physical address map. The underlying memory is also interleaved. It's a mess. You've got to talk to lots of bits of your system. There's no one place to tell, which is incidentally why that instruction is so bad on x86. So what did we do? We threw together a device class-like registration framework. Yeah, when I say device class-like, right now it is a device class. We had some feedback on that, which said you can only have a device class if you have an ABI to user space, and we don't yet. This is always flushed from within the kernel and very, very specific code paths because it's still expensive. Anyway, that exists. We'll clean that up. We register this with the architecture callback that already exists and is there being used by x86. That callback today, because the only implementation is the x86 instruction, doesn't actually have any ranges. It doesn't have a start and end, any of this stuff. So we had to add that, kind of straightforward. However, there is a bit of a trade-off here, because like any form of cache flushing, if you've ever done it for things like GPUs on non-coherent systems, there's a decision. You get over a certain size of flush, it's cheaper just to drop the cache, because that's a fairly clean operation. Just say, get rid of everything, rather than tell it to get rid of specific things where you've got to do a lot of matching and there's a sort of walk going on. Same thing happens sometimes on some of the hardware implementations here. So we actually need some way to control that, because if you're running on a shared system and you've got other VMs running, they don't care about your CXL memory, well, you certainly don't want to do the flush everything. Your new VM may take quite a while to come up because you're doing it the slow way, but it's not disruptive. Whereas if you're doing it for a machine that's running one workload, one big AI workload, and you want to get your model parameters in or whatever, you don't care. You just do the quickest. So there's a bit of a trade-off there, and we don't really know how to control that yet. Yep.
So the question is, I understand the problem. Wouldn't it be reasonably easy to solve it if the physical address of the device didn't change? I mean, I understand why it changed, right? Because you can hot plug a device or put more memory on the device, whatever. But I suppose you don't really need to look at the real physical address of the device from the CPU perspective. Like I'm just thinking about, for instance, NVMe cards, right? In theory, you have physical blocks in an NVMe card, but we know that that's not actually how it's implemented, right? It has a large bank and everything is mapped. And when you access the physical address, you are actually just accessing a table that reroutes you to some place. Isn't that the solution for this case as well?
Yeah, the DPA you're seeing here is not the physical address. It's a yet another layer of translation. So underneath that, and we'll touch a little bit later if we have time on sharing, there's a lot of craziness going on. Even the device physical address presented to multiple hosts could actually be a different address for the same physical memory. So a lot of that is going on. The problem is that translation thing is all about interleave control and the ability to do memory pooling. The reason that's different physical address is because you gave the stuff you were using earlier to someone else. And then someone else freed some and you pass it on. So it's kind of unavoidable if you're doing the pooling type situations. We also need it, obviously, for hot plug. And for, there's nothing you can do about it. It wasn't there. So, it's a good question, though. That bit's fun if we get into what is a device physical address. It's a lot of education to device manufacturers about that. It isn't quite what it's called. One of the issues with this is we're going to end up with a driver per implementation, potentially. There are no standards. So, after some chatting with ARM guys, we actually have a proposal to do this via a fake ACPI device. So at the moment it's whatever it is, ACPI 0019. And this uses the magic of operations regions and things in AML to allow you to do pretty much anything wrapped up in some interpreted language. We mapped this on top of the PSCI proposal that was an earlier generation of what was being discussed with ARM for how to solve this problem. That got dropped from the PSCI spec, but at least it was well thought out. So our proof point for a second test for this at the moment is a spec that was cancelled. So if anyone has another implementation that they'd be happy to talk about or point at documents for, any of that stuff, it'd be really handy because, yeah, okay, one that got dropped from a spec is kind of okay for proving the subsystem works. And obviously we have a real implementation as well, which is there in the code, which is ours. Anyway, interested to hear about that a bit later, but let's push on. Memory pull-in. So this is next generation hardware. It's probably not this year, maybe next year, maybe the year after, somewhere that sort of timescale, depending on whether you're talking about early deployment or mass deployment. This is all about solving the stranded memory problem. So when you're a hyperscaler and you're selling VMs to people, your customers are really annoying. They never want a fixed percentage of your server. They never want 25% of the CPUs and 25% of the memory. They want one VM with lots of CPUs and no memory, or very little memory, and they want another one with very few CPUs and masses of memory. And the reality is this means, and there's published data from, I think it's Microsoft, that says something like 20% of the memory in their cloud is unused by anyone. They do some caching stuff and things with it, but fundamentally it's just not in use, which is crazy and very expensive. So the solution that's proposed is you use disaggregated memory and you take maybe 20, 30% of the memory out of every server and you put it in a top-of-rack appliance and you connect that to all of the servers in that rack, which is usually 30-something servers. And this then gives you the ability to assign some slightly worse performance memory in to make use of leftover compute resources. Now, these are kind of the cheap VMs. They are the people who are paying the minimum fee, but at least you're doing something with it. It's not just sitting there with CPUs that are unused. And this allows you to do some balancing. Use multi-headed devices because we want that low latency. And this is really for dynamic allocations, typically to sort of medium-term activities. That might be the VM case, but we also have what I tend to refer to anyway as specific application memory. So this is where you've got something like an AI workload, you've got a database, you know exactly how much memory it needs for its data set. You give it that much memory. It's got that. It's it. When that application closes, we give it back. Don't need it anymore. And this gets around a lot of the traditional problems with memory hot plug where it's now impossible to get it back. There is a kernel stack for this. It's not yet merged. If anyone's curious to why, I'm happy to chat about that offline. But yeah, it will come. There are some challenges. We've got new management concepts. We've got to wire this all up to the cloud orchestrators, all of this stuff. We've got to have a way of actually providing the memory. You've got to provision it. It's the same problems as any sort of VM provisioning, just an extra dimension. We already talked about the memory for one purpose. At the moment, the solution for how you do this through the kernel is DAX. It's kind of the only way that exists today. Problem is, it doesn't work with confidential compute because it is mapped in the hypervisor. We need to solve that. Then when we define these interfaces, if you're using application-specific memory and you run your VM on your host and you get this particular interface, we have to have that in a virtual machine too, because people don't like to change their software stacks. So we will need a virtualization solution for this. For the control plane, the actual memory plane is just, page tables. So it just goes through, and that might be, at the moment it's looking like it'll be emulated CXL. Okay, so memory sharing. Why? So this is one of the things. You've got this multi-headed device wired up to a whole load of different hosts. Well, who says only one host can see the memory? So why do we do it? Now, the big problems in large memory usage, or some of them are, cases where you have to duplicate memory. AI models are the classic, where every server that's running the inference workload has to have that 4 terabytes or 10 terabytes or whatever model parameters. Don't do that. Just put it on your top-of-rack appliance. Have one copy and serve it to everyone, and then you save that memory on every single server. Works nicely. Also sharding. So if you've got very high-performance databases, you typically have to break the database down into little chunks, run them on different servers, because the in-memory database has got to be in memory and it doesn't fit. And a lot of this data is read-only or very nearly so it works well. And yeah, there's some crazy ideas like zero copy live migration. I'm always curious to hear about that, what people think of that. It's the idea that if it's in the memory, you can just swap the host on top. But yeah, it's kind of a pipe dream at the moment. Okay, so yeah, one last architecture-specific thing going to come up. I think I'm overrunning by a minute or two. Software managed coherency. So yeah, the CXL spec supports hardware coherency. Memory manufacturers don't like building it. There's a couple of reasons for this. It requires extra transactions on the bus to maintain coherency. They're a little bit costly. Actually, the bigger problem is that tracking hardware for this on the device is a whole load of reasons why that's hard. Well, it's not hard, it's just very expensive. And it seems people are not going to build it en masse. And this brings a whole bunch of challenges. Don't do clean write-backs. That's a good piece of advice from another architecture. Things that can break things really, really badly. Yeah, we get on to a question of how does an application flush writes? So, yeah, classic use cases, producer consumer models, synchronization out of band. What is a point of coherence, which is a classic sort of ARM term defining where you flush to, and some of the instructions you can issue from user space will flush to the point of coherence. What does it mean if you've got multiple hosts, and where does it go? And this is a bit of a challenge at the moment. There are some solutions. We can declare that in the physical address range that's going to CXL memory, it always means the memory. This means you've got to flush further than you normally would. There's another concept that we haven't touched on for sharing. There's what's known as temporal sharing, which is you're not actually sharing it to multiple hosts at a time. What you want to be able to do is to move it. So there's only one user, but later there might be a different user. And for those cases, it looks, from the point of view of the hardware description, exactly the same, but the software knows which one is going on. So we have this sort of open challenge to how we get the performance for those cases, because we don't want to flush further than we need to, but enable the other cases. And that's kind of an open question at the moment. And as noted, I'm probably out of time. So I won't really comment much on here, other than the usual, what are your applications? Bring them and test them. Let's see how well it works. Yeah, there's a whole bunch of pitfalls. I actually put this in the abstract, but then Gregory Price, who's at Meta, wrote a really, really big description for LSFMM on this, on all the crazy stuff that has been built and all of the problems it's causing us. So it's worth reading that, and then don't do anything that's mentioned in all of that documentation. Yeah, x86 is a wild west when it comes to memory maps. And ARM is much nicer as far as I know. Yeah, but there's lots of work to do. So any questions?
So what about...
No. You've got to have a microphone. Thank you. I know you can, but it's a recording.
Okay. So what about heterogeneous systems? Are in your diagrams those SOCs? I assume they're all the same. What about, you know, a general compute node and a accelerator node and stuff like that? And also, this stuff fits into the chiplet architecture ecosystem also?
Okay, so let's do the chiplet one first. So chiplet stuff, some of the chiplet specifications allow for CXL as one of the coherency protocols that's used over the chiplet interconnect. I don't actually know much about it, other than I've seen that bullet point on the slide. Heterogeneous, obviously there's different types of heterogeneous here. You've obviously got, so some of the colored blobs on here are accelerators. So you do get a mix, you do get things like peer-to-peer communication between them. Also, for more heterogeneous, obviously once you get to rack scale stuff, no one said the hosts are the same. They all talk the standard protocol. You can mix and match anything. And you can do, in the newer standards, you can do the equivalent to disaggregated memory for GPUs, other forms of accelerator. Whether anyone's building them is not public knowledge yet. So, yeah, absolutely. We're just butting up against the start of the next talk, I think, if I've got the time right. Thank you very much. Oh, thank you very much.